participate in the section. So autopilot, get ready to respond to questions when they come. But I welcome everyone, all of you, to today's engagement. I mean, it's this, like the title suggests, it's based on statistical models. So it's not going to be very smooth sailing for some people. For people with some statistics background or that has done some quantitative courses before, this would be like a revision. But I've tried to, satisfy those that have some quantitative background, as well as those who don't have any background in statistics, but then I'll try to let them understand some of the intuition behind some of these complex statistics methods, when we have to apply them, how we have to apply them, how we need to interpret results, and things like that. And then for those that has quantitative background, at least there would be some level of, trying to understand from the theoretical point of view, some of the theoretical foundation or concepts that underpin some of these methods that we are going to learn in the course of this training. So there will be a lot of interactions. I would encourage people to have, if you have questions, you can alert me or you can put them in the chat, and then Joel can alert me, and then I can respond to them. I may also be having questions that I have for you. If I have questions that need responses, I'll be happy if so one or two people can unmute and just tell us the answers, or you could also just put the answers in the chat, and then I can read them out to everyone, and then we can have a discussion about of the responses that we receive. The course would be also based on R. We'll be using R for most of the demonstrations, how to, run these statistical models on data using the R statistical software. So that is why it's important we understand some of the foundation for some of these models, so that when we see the R outputs, we know why some of these outputs are there and what are they doing, so that we are able to interpret the results that we generate from our statistical software. So it's going to be a blend, but I'll do my best to make them as simple as possible. We would focus on just the main message and not go so much into the details, so that we don't lose track on what the actual importance of the concepts that we are learning are. So I believe with this background, we are all good to go. If you agree with me that we should go, just type something in the chat, or just give me a wave on the software so that I know that you are ready for me. I need as many people as possible. Great. Dennis, Victoria, yes. Ade Dapo, I see you. Really, Johnson. Oh, Mental Health Data Prize is also giving us a thumbs up. Silas, Rose something, I saw it, but it disappeared. Godfred, Silas, Grace. All right, thank you all for your responses. Michelle, thanks for the yes on the chat. All right, good. So now I am convinced that it's not just autopilot, but I have very great participants. Let's make this course very lovely. Ask questions, and let's learn together. All right. So a little bit about the course. So some of the learning objectives. So in this course, we are going to, we hope that by the end of this course, we all would be able to understand the concepts of generalized linear models. That when we hear about generalized linear models, what are they? Like, why are they called generalized linear models, and how are they different? And then we would learn some of the principles in terms of, okay, so if I want to do a generalized linear model, how is the model specified? How does the model look like? How do I estimate the model? What methods are available to estimate the models? And how do I interpret the results that I get from the models? And then we also try to gain some proficiency in terms of how do we use the R software to be able to fix the GLMs and then also assess them. The GLMs that we are using, the models that we are using, are they doing justice to the data that we have to generate the insight that we need to inform mental health policies? And then we would, have practical examples. We'll take some, empirical data, real life data, simulated real life data, to see how do we analyze them using these software packages that are in the R software, and how do we interpret some of the results. So we in all this, we are just we'll try to develop our thinking skills when it comes to model building, and at the end of the course, you realize that the procedures that we use when we talk about modeling in terms of model specifications, model estimations, model interpretations, fitting, analysis, etc., they are all very similar. They only deviate a little bit based on what are the assumptions that this particular model is using. And then based on that, how do we interpret? They may also deviate a little bit in terms of how do we interpret them. So all of these things will come out very clearly as we go from one type of a generalized linear model to another. Yeah, so these are our learning objectives, and we hope that by the end of this course, at least the first part of this course, all of these concepts will become very familiar to us. So to begin with, I know a lot, there has been a course on R that has already been done, and then also Python. So if you have some knowledge in these two packages, let me see by hands how many have used R or Python before, or any other statistical software. Great. Dennis has done that. Julius, Freddie. Okay, Freddie, so many of them coming here, and Nora. Okay, good. So we have quite a number of people that have used the softwares. Some just Python. So Python, sorry, unfortunately, I'm not going to do Python, but the concepts are very similar. So if you understand once you understand the concepts, you'll be able to get appropriate Python packages that would help you to, but then you still will benefit from model specification, model estimation, especially the interpretation of the various models. You still can benefit from, and then also the transition from Python to R is also it's not that difficult. The codes will be provided. We'll run through it together, and then you'll see that things will be very clear to everyone. Okay, so we are going to start with the first section, which is the introduction, just introducing the generalized linear model. How many people are familiar with linear models or regression models? Anybody? Regression? Yeah, I think there has also been a course on linear models. Yes. Or regression models. People like to call it that way. So yeah. So linear models are very common, and it's like the foundation for most of the statistical techniques that are available. And when do we use them? We use them for a number of situations where our outcome variable is continuous in nature. Okay, so we have different scale of measurements. We have continuous type data, and then we have the categorical type data. In the continuous type data, you can have the ratio or interval scale. And then if you have categorical, then we have the nominal and then the ordinal type of data. So for linear models, the focus has always been on your outcome variable. That is the variable that is of interest. What your investigation is about has to be measured on a continuous scale. So that means that the responses are in terms of numbers that could even have decimals in them as the main outcome, like taking measurements of the height of someone. So you can have maybe 163 centimeters, you can have 180 centimeters, etc., as the height of somebody. So those type of outcomes, we call them continuous outcomes. And then when we want to see how other variables relate to these continuous outcomes, then the common model that comes to mind is the linear models that we are very well familiar with. And we use them because they help us to establish whether there is a linear relationship between the outcome, which is a continuous, and then the independent variables, which can either be categorical or continuous. So you could also have explanatory, some people call it explanatory variables that are continuous or that are categorical or in any type of measurement scale. So it's a very common procedure, but then the challenge with using the linear models is that it's limited in terms of we can only use it, even though we are saying that it is used for continuous outcomes. The continuous outcomes must have, when you plot a histogram, they must be like, they should have like a bell shape. It should, the distribution should look like a bell, or they should be, some people say, okay, it looks like it's normally distributed. And so if you have data that is not normally distributed, then the linear models becomes inefficient. So it means that they may not do justice to your data, because the model itself makes that assumption that your data should be normally distributed. So if you have data that is not normally distributed, then we have that limitation. What some people do is that if the data is not normally distributed, what you can apply some transformation. So maybe I can take the log of the outcome. So just take the log, and then when you plot the instead of plotting the actual outcome, when you plot the log of the outcome, you would find that it's symmetric in nature. And so once that is done, then you can build a linear model not on the original data, but on the log transformation of that of the original data. And in that case, you still can build a linear regression with that. The only challenge is that some of the transformations would hinder in terms of interpretation. You may not be able to interpret the models, intuitively, because now instead of saying maybe there is a difference in the height between males and female, if you've taken the square root of that, then your interpretation will be like, okay, so now there is a difference between the square roots of the heights between males and females, and intuitively that doesn't read very nicely. Okay, and so these are some limitations that we encounter when we apply the linear models. Apart from that, the linear models also make certain assumptions, which you are very much familiar with. Okay, we have the assumption, we've talked about the assumption of normality, that your data should be normally distributed. So when your data is not normally distributed, then you are done. It means that your model will not work. There are assumptions like constant variance. So constant variance, it's saying that for every level of your independent variable, the variance in your outcome is constant. And this is one of the assumptions that are very, very difficult for you to satisfy. You may be able to get your data to be normally distributed, but then when it comes to the assumption of constant variance, you would see that it is possible that this assumption will be violated. Which would mean that you need to have, models that would account for varying variance of your response based on the level of the independent variable. Another assumption that the regression model makes is that your data is independent. So this assumption, oftentimes, it's based on the type of research that we are doing. This assumption is always like it's often met because I'm collecting data on individuals, and individuals are independent of each other. I'm performing an experiment on housing, and each house is independent of each other. So these assumptions, even in terms of verification, you don't need to use any complex statistical method to be able to verify this assumption because they happen in practice. Like you would just know by the way you collected your data that the data is actually independent. However, there are certain studies where even though the individuals are independent of each other, the responses that we measure continuously. We can measure, let's say, my blood pressure now, and then my blood pressure in 1 week's time, my blood pressure in the next 3 weeks. Okay, but another person could also have their blood pressure measurements taken also today, next week, and then the next 2 weeks. All right. So even though I am independent of that person whose blood pressure has also been taken, we are independent, but then the responses that are measured are no longer independent because they have taken measurement on me multiple times, and so that introduces what we call dependency. And so if I have that kind of data, then my linear models cannot help me because my linear models are assuming that my observations are independent. However, by the nature of the way I collected my data, that independent assumption is violated. Another example is when you have surveys that you are conducting on, let's say, children who are living in the same household. So if I pick one household and I compare to another households, they will be independent because they are different households. But now if I consider the measurements that are coming in from some children who are in the same households. Okay, so let's say maybe I'm talking about their weight, the weight of these children, or whether the children have stunting or not. Because they are coming from the same households, the measurements that I'll take from them cannot be said to be independent, right? Because there is some dependency. They eat from the same bowl, they live in the same environment. So the measurements that I'm going to get from those individuals within the same households, I cannot say that they are independent, all right? There is some form of dependency in that. And so when you have that kind of situation, then the linear models breaks down. You cannot apply the linear models any longer because this assumption has been violated. And then another assumption is that there is a linear relationship between the variables. So it makes an assumption that the independent variable and the dependent variables, the relationship between them is linear. But it's possible that you can have a non-linear relationship between the independent and the dependent variable. If that happens, then again, the linear models breaks down. It means that we can no longer apply the linear models. Okay. All right. So these are some of the limitations that I have mentioned. There are several other limitations that linear models are associated with linear models. Is there anyone who wants to tell me any other assumptions that I probably have left out for discussion? You can use the chat or you can just unmute. Any assumptions that is made by the linear models that has not been talked about? Yes, I want
How
both
about,
people.
sorry, Edie. How
Yes.
about the errors, normality of the errors that you make on the measurement, versus the model against the, in other words, the prediction versus the actual?
Exactly. Actually, when I talk about all of these assumptions, the models themselves make these assumptions through the error terms. So it is the error
Yeah.
term that is normally
Okay.
distributed, and that is why we have to
Exactly.
make sure that the responses are normally distributed so that you can achieve that when you compute the residuals. And then it is the same error that we assume that it has constant variance, the same errors that we assume that they are independent, etc. So yes, so the assumptions are placed on the error terms, but when you have your data, you don't have the error, right? You only have the observations. And so the explanations that I'm giving is in terms of, okay, if I have data that looks like this, how do I go about it? So great. I have seen Freddie and Lemesa, great points. Yes. Linear models also makes an assumption that our data does not have outliers. All right. And the implication is that when we have outliers in our data, then we are going to violate most of this assumption, because once I have an outlier, it will be very difficult for me to achieve normality. It will be very difficult for me to have constant variance. Okay. So these two assumptions will be violated if I have outliers in my data. So again, it means that linear models will not do very well when you have outliers in your data. So if you have data that has those type of characteristics, then the linear model is not a good option. Now Autopilot has put in so many things. I have missed the other one. I think he said there should be no multicollinearity. All right. So the independent variables, so the linear models, when you fit the linear models, the independent variables should not also be correlated. And that is one assumption that the linear model does. So if I have maybe as an independent variable, I have maybe the wealth of people that I have quantified. And then I also have another variable, which is, let's say, income. You know, wealth and income kind of maybe measuring the same thing. Maybe one is just a proxy of the other. So if I'm building a model and then I put income and wealth together, then I am violating that collinearity assumption, or the assumption that my independent variables should not be correlated with each other. Okay, so yes, so great. There should not be collinearity between the explanative variables. You need correlation only between the outcome and the independent variables, but you don't need correlation between the independent variables. And that is also one assumption that the linear model makes that needs to be verified. Bonventure, you had your hand raised. Could you go ahead with your question?
Hey, sorry, Samuel. I think I just pressed long way. I didn't wait. Sorry.
Okay.
Please
All right,
continue.
great.
Thank you.
Okay, so yeah, so we've seen why the linear model may not be a suitable model for a number of reasons, or a number of things that if they are violated, then we cannot apply them. And there are certain types of data that when we collect, then obviously all the assumptions that we have mentioned are likely to be violated. So for example, so we call them, we call them non-Gaussian outcomes. So data that is normally distributed, we say that normal distribution is Gaussian. All right. So these are just terminology. So when I use the word Gaussian, I'm just saying a normal, that the data is normal. But if I say non-Gaussian, then it means that the data is non-normal. So there are certain kind of data that when we collect, naturally, they are not going to be normally distributed. Like binary data. I have, do you have diabetes? Yes or no, right? The only information I have about this outcome is yes or no, yes or no. So if I do a graph, then I'll just have 2 points, yes and no, and then some points just on the same level. There is no way that kind of data would follow the normal distribution. All right. Or counts. So if I have maybe I pick a household, how many children within a household has how many people within the households had diabetes. All right. So it means that I have to go to the households and know, do you have diabetes? Yes, no. Do you have diabetes? Yes, no. Do you have diabetes? Yes, no. Then I'll count how many of them in that household has diabetes. Okay. So that gives me a count data. All right. And that count data, oftentimes count data would not follow the normal distribution. All right. And then we also have some types of outcomes that we measure, such as time to event. So time until somebody dies, okay? Or time until somebody progresses from a particular condition. So maybe cancer. Time until you develop cancer, okay? Or time until somebody relapse from a particular surgery. So maybe somebody has done some kidney surgery. We want to measure the time until the person relapse and things like that. Such data oftentimes would not also follow the normal distribution. All right. So it means that if I collect data like that, even though time to event data may look like it is continuous data, if you attempt to fit a linear model, you would find that most of the assumptions will be violated. The same as the count data. And for count data, one of the key things is that you may have a count that has so many zeros. So like the example that I gave, I go to a household and I count how many people have diabetes. I could have maybe 100 households that there's nobody there that have diabetes. So the zero count would have so many respondents compared to all the other, maybe those who would say they have one or two people who have diabetes. And so that type of data cannot be normally distributed. So all of those type of outcomes that naturally would not follow a normal distribution, statisticians have developed very special methods to be able to handle them, so that some of the assumptions that we needed for linear models would not be needed anymore. And so we have this class of models which we call generalized linear models, and that is what we are going to focus on. So the generalized linear model is all the other type of models that we are going to use when our outcome is not normally distributed. Okay, so if we would fit a model for binary or binomial data, we can get a model for count data, we can have a model for time to event data, etc., etc. All of those models, which we'll come to in details, they all form part of what we call the generalized linear models. Okay, now these generalized linear models, just like the continuous in the regression, we say that the outcome, which is continuous, follows a normal distribution. For the non-Gaussian outcomes, we would say that they are the distribution that they follow is the exponential family of distributions. Okay, so the exponential family of distribution is just one family of distribution that can be used to handle all the different types of non-Gaussian outcomes. Okay, so that is the key message. So we would see examples like for binary data, we use the binomial distribution or the Bernoulli distribution. Count data, we use the Poisson distribution. Time to event data, we can use the exponential distribution, or we can use the Weibull distribution. All of these distribution, they form part of what we call the exponential family of distributions. Why do we say that? It means that all of these distributions, we can write them in this form. All the distributions that I have mentioned, we can write them, or we can describe them in this form. We can write all of those distributions in this form. And so that means that we have, what defines this exponential family is that we have two types of parameters. One which we call the canonical parameter, and then one which we call the dispersion parameter. The canonical or the natural parameter, or the dispersion parameter. So just take note of this. That is the message we want to get from here, that if I have an exponential distribution, if I want to know whether my distribution is part of this family, then it must have two parameters. One should be the natural parameter, and the other one should be the dispersion parameter. It should also have two functions, okay? It should have two functions, one function that relates to the natural parameter, and then another function that relates to the both the dispersion parameter and your data. Okay, so not so important for this, but just for those who want to understand the foundation and why these are all put together as one class of modeling. Okay, so remember, canonical parameter and the dispersion parameter is the key message. And for every distribution, we can describe every distribution in that we have using two things, or mostly two common things. We can calculate the mean and the variance, the mean and the variance. So if you look at the linear models which we are coming from, the linear model that assumes the normal distribution. The normal distribution has two parameters. It has the mean and then the variance. It is the mean that we model, and it is the variance that we say that the variance should be constant, right? When we were discussing the linear models. So it means that these two parameters describes every. So if I have any distribution, the first thing that should come in mind is, so I need to know three things. I need to know the name of that distribution. I need to know what is the mean of that distribution, and then what is the variance of that distribution. The first two are called the moments. The mean and the variance, we call them moments. So when I mention moments, I'm referring to either the mean or the variance. Okay, and then the reason why the GLMs are different comes from here. All right, the reason why the GLMs are different or are unique comes from these two relationships, that I look at the mean and then I look at the variance. Okay, and then so we call that the mean variance relationship. So the mean variance relationship is given by this expression. Okay, so the variance depends on the mean function. So you can see from here, and a dispersion parameter. So the dispersion parameter that we talked about. So there is a relationship between the variance and then the mean. Okay, there is a relationship between the variance and then the mean when we talk about the exponential family, and that relationship is given by this. Now, why is the generalized linear model different from the linear model? The normal distribution actually happens to be also a special case of the exponential family. So if I look at the normal distribution, I can actually write the normal distribution also in this form. So that means that the exponential family is just not describing just the binary, the count, the Poisson, the other distributions, but actually the normal distribution is also a special case of the exponential distribution. So then the question is that, then is linear regression also a GLM? Is a normal regression, the normal regression that we know? Can we then say that then it is also part of the GLM? Because the GLM, we are saying that they follow a distribution which we call the exponential family. So if the normal distribution is just a special case of the exponential family, then why do we say that the GLM, why is the normal, the regression different from here? All right. Now, the key thing is that for the normal distribution, when we write the mean and the variance, the mean and the variance are described by two different parameters. Okay, two completely different parameters. The mean, we use the mu as the mean, and then the variance is sigma squared. So there is a disconnect. There is no connection between the mean and the variance. However, for the other members of the exponential distribution, so like I am shown here, so we are going to focus on the last two columns, rows, all right, that when I look at the continuous, or the one which is the normal distribution, its mean and variance, the mean is mu, but the variance is sigma square. Mu and sigma square are completely different, right? So they are separated, okay? But when I look at the binary, the mean and the variance, the mean is pi, and the variance is pi over 1 minus, pi times 1 minus pi. So it means that if somebody tells me what the mean is, then I can also tell the person what the variance is. I'll just do the calculation. I'll just take the mean, and then I'll subtract 1 from it, right? The same with the Poisson. Poisson, if the mean is lambda, and then somebody asks you, okay, I have a distribution, the mean is lambda, what is the variance? I already know, because the variance is the same as the mean, okay? So here, there is a direct mean variance relationship between the binary and the counts, okay? Whereas for the normal distribution, the mean and the variance are completely different. If somebody tells me the mean, there is no way I can tell the variance, and vice versa, all right? So you tell me the mean, I cannot tell you the variance. But for the other distributions, which typically, and that is what most people classify as the generalized linear model, is that when somebody tells me the mean, I can tell the person what the variance is. When you tell me the mean of the Poisson, I can tell you what the variance is. Okay, so we call that the mean variance relationship. Now, when it comes to the modeling as well, I talked about the natural parameter. The natural parameter for the continuous is the mean. So if I pick the continuous function, the natural parameter is the mean. And that is why when we are fitting a linear model, we just take the mean and we relate it to the independent variables. So I have gender, I have age. So I just relate the mean to the independent variables. But for binary, the natural parameter is you take the log, and then we take the probability pi divided by 1 minus pi. Okay? And it is this natural parameter that we have to relate to the independent variable. And then for count data, we also have the log of the mean, which is the lambda. That is what is the natural parameter, which we have to relate to the independent variable. So anytime we are fitting a regression, a GLM, if it is the outcome is binary, we should know that the independent variables, the interpretation of the parameters are in terms of these transformations, which are part of this natural parameter. We will go into details. So this is the part where I give you the theoretical background, but we'll pick each one of them, and then we'll delve deeper into it, and then we see what I mean by that is what we relate to the independent variables. Now, what is the use of this natural parameter? If I take the continuous, if I consider the continuous outcome, right? Like a height, you know, height is a continuous variable. So it ranges from minus infinity to infinity. I can have I can have positive numbers in this case. I can have from 0 to maybe positive infinity. So it has a wide range of values that I can pick. And then the independent variables, we had mentioned that for the independent variables, which are always on the right-hand side of the equation, we can have so many independent variables. So we can have continuous variables, we can have categorical variables, etc. So if I take the mean of the continuous and I equate to the independent variables, then I am putting all of them on the same scale. So I can measure this one from minus infinity to infinity on the left-hand side, and then minus infinity to infinity on the right-hand side of the equation. Okay, so let me pick one equation, and then I can explain what I mean by that. So example is on the right-hand side of this. So on the right-hand side, I have x1, x2, so many, I can add so many independent variables. Okay. And then for the linear regression on the left side, it is already y, which is continuous. So I can pick the continuous variable and equate it to a continuous variable. Okay, so continuous on the left hand side, continuous on the right hand side. But for the GLMs, if I use the mean, so if the mean is pi and I equate it to the independent variables, then I have violated that equation, because probabilities lies between 0 and 1. Probabilities always lie between 0 and 1. And then on the right hand side, I have continuous variables, independent variables, which will be measured on minus infinity to infinity. So it's continuous. So I have continuous on the right hand side of the equation, but I have between 0 and 1 on the left hand side of the equation. So I cannot equate them. So for me to make sure that the left-hand side of the equation is also from minus infinity to infinity, so that it becomes continuous, and I equate it to continuous on the right-hand side, I take this, that is why I apply this natural transformation. So I'll take the probability which lies between 0 and 1, I'll divide it by 1 minus the probability, and then I'll take the log of that. So when I take the log of that, then the values that I'll get from here can now range from minus infinity to infinity. So in that case, I have made the left-hand side minus infinity to infinity. I have made the right-hand side minus infinity to infinity. So then I can I can fit the model. The same with the counts. So count data always start from 0 up to infinity. But on my right-hand side, I can have negative values. I can have negative 1, negative 2 on the right-hand side. So I need to make sure that the left-hand side is also ranging from minus infinity to infinity. So how do I do that? Because the values of lambda is 0 to infinity, I'll just take the log of that so that it also becomes minus infinity to infinity. And then I can equate it to the independent variables that will be on the right-hand side of the equation. Okay. Is there any question, any clarification that you need from here? So the things that I have mentioned are the type of distribution that we need to mention, the mean of each one of them and the variance. Note that for the continuous variable, the mean and the variance are different, but for the other non-Gaussian outcomes, the mean depends on, the variance depends on the mean. So if somebody tells me what the mean is, then I know what the variance is. If somebody tells me what the mean of the count is, then I can tell the person what the variance is. Okay. And then in terms of how do we fit the model, we have to make sure that we pick the natural parameter, and it's the natural parameter that we relate to the independent variables. And how do we get the natural parameter? The natural parameter is just helping us to make sure that on the left-hand side of the equation, we have values that are ranging from minus infinity to infinity, which we can equate to the right-hand side of the equation, which would have values also from minus infinity to infinity. Any questions? Anybody with a burning question for clarification? This is the most difficult part of the course, but once these concepts are done, then we are good to go. The rest of the course will just be building on, I'll just be repeating all the things that I'm saying for all the different models that we'll be considering. Okay, if there are no questions, let me proceed. All right, so now we are going to talk about the GLMs. So we have seen how the GLM is. So it means that when we talk about GLM, the distribution that we are considering is called what? The exponential family. So if you go to the software, sometimes you see that the term exponential family is what is used in some of the softwares. And it is introduced by statisticians to address some of the limitations that we have seen from the linear models. because they do not make any severe assumptions. You don't need to have a very strong assumptions for you to apply them. They are very flexible. They can also be used to handle nonlinear relationships. Unlike in the linear regression, where we said the relationship between the outcome and the independent variables should be linear, here, even when they are not linear, you can still apply them. And the advantage of the GLM, like we have seen, is that they are very flexible. They can handle any type of response that we have. Okay, we can handle the binary type, we can handle the count type, we can handle the time to events, we can handle any type of, we can handle the ordinal. Even if we have outcomes that are ordinal, we still can apply the GLM approach. And then it uses what we call a link function. Remember when we were talking about the natural parameters, okay, when I was mentioning the natural parameters, I said we use this transformation, all right? And that transformation is what we call a link function. So what I have is the mean, okay? But I apply this transformation so that I'll be able to make my response move from minus infinity to infinity. So we call that a link function. And that is how it handles that, also handles that non-linearity. And then we don't need to have the assumption of constant variance, right? Because we saw from the variance for the continuous, we have different parameters for the mean and different parameters for the variance, for the continuous outcomes. But when we saw from the categorical, the non-Gaussian outcomes, there is always a mean variance relationship. So it means that assumption of non-constant variance is not really that important. So just an explanation on what the length function is. So the length function is what we are going to use to connect our linear predictors to the mean of the response. So that is what we have seen above, that we can connect. If we want to connect them so that we have from minus infinity to infinity from both sides, then we need what? A length function. So it means that anytime we want to fit a GLM, these are the things that we need to remember. So I'm going to list them. Anytime we want to do a GLM, we need to first understand what our response variable is. So if we identify our response variable, we are going to link that response variable to which distribution can we use. We would know that if it is not continuous, then it has to be one of the exponential family of distributions. But which of them? If the outcome is binary, it is the Bernoulli. If it is count, it is Poisson. If it is time to events, then you have more options. You can do the Weibull, or you can apply the exponential distribution. And these are options that are available on the software. So you need to make a decision before you can apply the software when you want to fit a GLM. And then you have to also, once you have specified what's your distribution, you need to know what length function can help you to connect the linear predictors to the mean of the response variables. Okay, so these are very important key things that you need to remember. Now, there are a number of length functions that you'll be required, even if you are using the software, you'll be required to specify when you want to fit a GLM. Okay. The first link function is called the identity link. So the identity link is like no link at all. So you would see that, and that is applied to, we said the normal distribution is one of the examples of the exponential family. All right. But you see that the mean is already mu, but the variance, the natural parameter is still mu. So we have not applied anything. So we call it the identity. All right. But for the other ones, the mean is pi, but we have applied a transformation, which is log of pi over 1 minus pi. This one, the mean is lambda, but we have applied log of lambda. Okay. So when we talk about the identity link, it's like we are not applying any transformation at all. And that is only applicable to the normal distribution. And the reason why I'm mentioning this is that there are some softwares like you see in R, maybe the package is called a GLM, all right? The name of the package is called a GLM, but it doesn't mean that you cannot use it to fit a regression model. You can still use that same package to fit a regression model, but you have to remember that when you do that, you have to specify the distribution as normal distribution, and then you have to also specify the link function as identity. You have to tell the package that, no, this is a normal distribution, but I'm using the identity link. That means that I don't want to do any transformation because my data is already continuous. Now, when it comes to the binary or the binomial distribution, we have options. We have a link function, which we call the logit link. All right, so we use the logit link, we apply it on the mean so that the values moves from minus infinity to infinity. Then we can relate it to our independent predictors. We also have another transformation called probates. So the probates I have not described here. So the ones that we saw from the what we saw from this here, the log into bracket pi over minus pi is what we call the logit link. All right, the link function we have applied here is called the logit link. So the logit link takes the probability, divide by the 1 minus the probability, and takes the log of that. So that is what we call the probate, the logit link. But we also have another way of changing our observations from 0 to 1 to minus infinity to infinity, which we call the probate link. I'm not going to describe that, but it is one of the options that are also available that you can use when you are fitting a binary, when your outcome is binary. And then we have the log link. The log link is for the Poisson distribution, or if you have count data. So if I have count data and I want to model it, then I have to make sure that I specify the distribution to be Poisson, and then I specify my link function as the log. Okay, and like I have mentioned before, once we use the link function to transform the mean, then we would then relate it to our predictors through a linear combination. So we just pick a linear combinations and then we apply. So this is how the link function operates, assuming that I'm going to use the binary outcomes. So if I maybe I'm predicting the probability of depression occurrence based on some risk factors. Okay, so that is my objective. So I want to predict the probability of somebody having depression based on their risk factors, maybe their age, their gender, etc., etc. I know that because I'm interested in the probabilities and I'm getting values which are 0 and 1, the 0 and 1, I cannot relate it to age, which is age is 200. There is no way 0, 1 will be equal to 200, blah, 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 blah. So I need to do a transformation. So I'll apply a link function. And that link function for binary data, we have mentioned the logit link, and then we have also mentioned the probate link. So the logit link is one of the examples that I can use. And then for the risk factors, I need to have a linear combination of the variables. So just like we have in regression, in linear regression, the left-hand side would have been y equals beta naught plus beta 1 x1 plus beta 2 x2. And these beta naught, beta 1s, they are the coefficients that will tell us whether there is an effect of the x1 and x2 on our outcome. So it is the same way. The moment you apply the logit, the length function on your mean, then you are almost like doing the same thing as you have been doing in the regression. So the only thing is that we are applying some transformation on the probabilities. And then the coefficients, we will see later on that on how do we interpret them. For a linear model, the interpretation is straightforward because we are just relating this to the mean directly. So it means that there the interpretation is easy, but here we are relating it into a transformation of the outcome. So it means that if we want to interpret this correctly, then we have to do some try to understand how these interpretations can be done. And we will see later on that these betas is what we usually convert into what we call the odds ratio, which we then interpret and present in our reports. So we'll see further details on that later on. So this is just a general, both theoretical and intuitive understanding of what the generalized linear the generalized linear models are, why we need them, and what are the components when we want to fit them. What are the things that we need? What are the ingredients that we need to be able to fit these kinds of models? Now we are going to pick each one of them and go through all the processes that I have described, go through all of them again, and then we try to see how do we interpret them, how do we fit them, and how do we apply all the various methods. Is there any pressing questions from anyone before I start with the next section? If you don't want to speak, you can type your question on the chat. Salas is okay. He thinks everything is good. All right. So the first generalized linear model. So remember we said the generalized linear model is just a general class of models. So there are so many models that sits under what we call the generalized linear model. The logistic regression is one of the simple ones, and I'm sure most of you have applied it, but now you are getting the some of the intuition behind why the logistic regression is different from the linear regression, and why some of the times when you are fitting them, you need to specify or make some certain specifications before you can fit them. So we are going to focus on the regression models into details. So the logistic regression is one of the GLMs which we apply when we have binary outcome, when our main outcome of interest is the binary outcome. And we usually use the logit length function. But today we have seen that we can also use another length function, which we call the what? The probit length. Okay. The most common one is the logit length because it has very nice way of interpreting the coefficients. So people like it so much. And that is why it is the most popular one. But then there are also other length functions that one can apply. And when do we need the logistic regression? So assuming that we want to predict the likelihood of a person developing depression based on certain demographic variables, right? Because the outcome variable is, likelihood or probability, it's binary in nature. It's either you are developing depression, yes or no. Then we would think of what's a logistic regression because the outcome is binary. So an example of assuming that in our data, we have the person's age as one of the independent variables. We have the person's gender, we have the income of the person, and then we have the depression status, which is binary in nature, yes or no. And mostly the yes, we assign a number 1 to yes, and then the no, we assign a value 0. So yes is 1, no is 0. So what we want to model is that we want to model the probability. What is the probability that the depression status is equals to 1? Okay. So what is the probability of somebody getting what? Depression. So we call that probability, I'm going to call it here P. I have called it pi before, but it's the same thing. Here I'm calling it what? P, which is the probability that somebody is having depression. Okay. Now, a number of concepts that we need to understand. Anytime I have a probability of an event, so probability of, let's say, getting depression, and I divide it by the probability of not getting depression, we call that the odds of depression. what are the odds of depression? So the odds of depression is what is your chance of getting the depression divided by what is your chance of not getting depression. So in another way, it is the probability of getting depression divided by 1 minus the probability of getting depression. So 1 minus the because there are only 2 events, the probability of getting the depression plus the probability of not getting depression will be equals to 1. You have to be in either way, whether you have it or you don't have it. There is no middle point. Okay, so it's the probability of your odds of you getting depression divided by the probability of you not getting depression. We also call it the probability of success. Getting depression here is not success, all right? But yeah, for some events which are binary, when we say success, it means that it's a good thing. So you may find some definitions that says the probability of success divided by the probability of failure, depending on what you are modeling. In this particular case, if our interest is we want to model the probability of failure, then we'll define our odds as the probability of failure divided by probability of what? Success. All right, because then our focus is on we want to predict the probability of failure. That is our main outcome of interest. So that is what we call the odds. So you probably have seen this, the probability of something occurring divided by 1 minus the probability of that thing occurring, when we talked about the canonical variable. So I'll always come back to this. So you see that I had here the natural parameter. I have pi over 1 minus pi. So what I was actually doing was that I was taking the log of the odds. So instead of saying pi over 1 minus pi, now I can come back here and say, okay, when I want to do a binary or logistic regression, I'll just take the log of the what? The odds. And where the odd means that it is the probability of success divided by the probability of failure. Okay? So so that is it. So we are just applying the log, not on the probabilities, but we would see that we often would apply the log on the what? The odds. And then once we apply the log on the odds, that is what we call the logit. Okay, so now we know what logit is. Logit is simply what? The log of the odds. And what is the odds? The odds is the probability of getting the event divided by the probability of not getting the event. Okay, and then we had said that why do we do this? Why do you have to take the log of the probability? It's because we want we are going to equate this side to linear predictors. So we want them to vary from minus infinity to infinity. So this transformation would help us to transform our outcome so that they fall between minus infinity to infinity. So you can see that I'm just repeating most of the things that I have said, and it would keep on like that because now we understand what the general framework of generalized linear model is. Then now what we call the logistic regression is now taking the logits of the probability of the sources, and we relate it to the linear combination of the independent variables. Okay, so we are now back to like the regression. So the logits will be equals to beta naught, which is the intercept, plus beta 1, which is the coefficient of age, plus beta 2, which is the coefficient of gender, plus beta 3, which is the coefficient of income. So then I'll be able to interpret what is beta 1, what is beta 2, what is beta 3, in terms of how do they relate to the probability of me getting depression. Okay, and then according to this definition, we have said that the logit is just the log of it's just the okay, so there is a typo here. So we said the logit of pi, we have defined it here, is the same as the log of pi over 1 minus pi. So the log should be standing outside. So it's supposed to be a log into bracket p over 1 minus p, because we said p is the probability of success and then 1 minus pi will be the probability of failure. And then whatever is on the right-hand side remains the same. Okay? Okay. All right. Now we want to see if we have formulated, if we have specified our logistic regression like this, and we fit a model using our software, the software will be giving us some values, which are the beta naught, the beta 1, the beta 2, the beta 3, because the age, the gender, and the income, we have it from our data because we collected data on them. And they are the ones that we are going to use to determine what is the value of beta naught, what is beta 1, beta 2, beta 3. So that means that the software is going to give us results of these parameters. And what is important is how do we interpret them? So we are going to go through very simple ways of how do we interpret models. And the approach that I'm going to give you, you can apply it to any type of model, any type of model. If you want to, if the model is specified, and you want to see how do you interpret the coefficients, you can always adopt this approach. Okay, so how do I interpret the coefficients? I'm going to interpret the coefficients like this. First of all, I'm going to pick 2 individuals from my data. Okay, and then I'm going to assume that these individuals, the first one is A, and then the second one is B. All right, and they are all in the data. I don't know whether they have depression or not. All I know is that these are 2 individuals. Okay, so I can say that these individuals, their exposure, I'm going to define their exposure to be 1 if the person has is exposed to a particular condition, or 0 if the person is not exposed. So let's assume that in this particular case, the characteristics of these individuals are maybe have they been exposed to smoking? Okay, so I have 2 individuals. I want to know whether they have what is their probability of getting depression, but they are exposed to certain conditions. So maybe one of them is exposed to smoking, but the other person is not exposed to smoking. Okay, so I'm creating an independent variable, which is X, which I'm going to give 1 if the person is exposed to smoking, and then 0 if the person is not exposed. Now I'm going to distribute this. I'm going to say that it is the person number A, the 2 people that I have chosen. The person number A is the one who is smoking, but the person number 2 is not smoking. Okay, so that is now my situation. I am fitting a logistic model to model the probability of getting depression. Now I have picked 2 individuals. These 2 individuals, they have smoking status. The first person, I'm going to assume that they smoke. And then the second person, I'm going to assume that they do not smoke. So in that case, I can write the logistic regression that we described separately for individual number A, and then I also write the logistic regression for individual number B, because they are 2 different people, they have different risks. So I'm going to call PA is the probability that the person who had the person number A, what is the probability that he gets depression? And then PB is the probability that person number B also has depression. I want to see their depression status. So in that case, my model will be beta naught plus beta 1 times X, right? That will be my logistic model, because I only have 1 independent variable, which is their exposure to smoking. But I said person number A is smoking. So smoking, the X is 1. So instead of putting X here, I'm putting 1 because that person is smoking. Okay. And then for person number 2, I said he's not smoking. So the X value for that person is 0. Is that clear? So this is the logistic equation for person number A. and this is the logistic equation for person number B. Now, what do I do with this information? Now, I can subtract these two equations. I can subtract equation A from B. So assuming that this one is equation 1, and assuming that this one is equation 2, I'm going to subtract the 2. So I'll take the logit of PA minus the logit of PB. Then if I subtract the right-hand side, beta naught minus beta naught, what happens? Goes to 0. And then here, beta 1 times 0 is 0. So when I subtract, what do I get? I'll get beta 1. Okay? So it means that when I do that subtraction, I end up getting the logit of PA over the logit of PB equals to beta 1. Now, this is going to help me to interpret what beta 1 actually is. All right? Now, we know what the logit of PA means. We have defined the logit. We said that the logit means that it is the log of the odds. The log of the odds is what we call the logit. What is the log of the odds? The log of the probability of A getting depression divided by 1 minus A not getting A getting depression. And then we do the same because this one also say logit for the person number B. So we do the same thing. So probability of PB over 1 minus B. And then beta 1 was there, so we still have our beta 1. Now I'm going to write this one because we said that this thing PA over 1 minus P means the odds. So it means that the first one is the odds of A, and I have two logarithms. If you have two logarithms that are subtracting, it means that you can divide them. Okay, so I have the log of the odds of A minus the log of the odds of for B, and that means that I can keep one of the log and then I'll divide them. So this one means that I have the log of A of the log of the odds of for A divided by the log of odds for B, and it is still equals to what? My beta 1. Okay, now I have log here. If I want to get rid of the log, then I'll take the exponent of both sides, so that what will remain here will be the odds for A divided by the odds for B, and it's equals to the exponent of what? Beta 1. So the exponent of beta 1 is the same as the logs for the odds for A over the logs for of B, and we call that the odds ratio. It is the odds ratio, the odds for person number A divided by the odds for person number B, and it's a ratio, so we call that the odds ratio. So the odds ratio is equals to the exponent of the coefficient of the x1, which is whether the person is smoking or not. So this expression can help me to interpret. So it means that anytime I fit a logistic regression and I want to interpret them in terms of the odds ratio, then I will have to take the exponent of the coefficient. I will not interpret directly what the beta 1 is, but I would what? I will take the exponent and then interpret it in terms of that. So what does this mean? So it means that if I want to interpret beta 1, then this is how I go about it. I will say, because I can cross multiply, odds for A is equals to this value times the odds for B. So the odds, so we interpret this as the odds of the outcome for A. So that means that the odds of getting depression for this person A is this value here times the odds of getting depression for person number B. So it means that if I have two persons and then I want to interpret the coefficient here, what I'll do is that I'll take the exponent of that. It gives me a value. And then based on that value, I can say that the odds of the first person is this times the odds for the other group of persons. Okay, so let's see. Now, how do we interpret that e to the power beta naught, beta 1? if we fit the model and beta is equals to 0, if beta is equals to 0, then what do we have here? If beta is equals to 0, then I'll have e to the power 0. And any number raised to the power 0 is what? Is 1. So it means that what I'm saying is that the odds for A is the same as the odds for B anytime this beta 1 is 0. And that is what we have here. So anytime the beta is 0, that means that if it is not significant, if beta 1 is not significant, then it means that the odds of the outcome for the exposed and the unexposed is the same. So that means that there's no difference between whether you are smoking or whether you are smoking or not. If the this coefficient here is almost 0, oftentimes it will not be exactly 0, but you see that it's very close to 0, and it is not and statistically it's not significant. Okay, then it will be very close to 0. In that case, we will say that, okay, then it means that the odds for getting exposed and the odds for not getting exposed is the same. However, if this value is very big, that is, if it is bigger than 0, then what we will see is that when we take the exponent of the beta, it will be bigger than 1. Now, when it is bigger than 1, then from that expression that we have here, it means that the odds of A would be bigger than the odds for B, because this value is bigger than 1. And what does that mean when it comes to interpretation? It means that the odds of the getting depression for the exposed person is greater than the odds of getting depression for the person who was not exposed. So in this case, smoking would lead to higher odds. So remember, odds is the probability of getting the condition divided by not getting the condition. So you can also interpret it in terms of your chances of getting, or your likelihood of getting depression. So it means basically that the chances of getting depression is larger for the unexposed group than for the exposed group. And when we find that this is less than 1, so if I say beta is greater than 1, then greater than 0, it means that the value is positive. So it means that when I look at the coefficient, the raw coefficient, it is positive. If it is positive, then it means that when I calculate the odds ratio, it's going to be bigger than 1. But if it is less than 0, it means that that value is negative. So you may be seeing some coefficients that are negative values. Those negative values means that the outcome for dispersion is lower for the one that we pick as the numerator, which is the probability of the odds of getting depression divided by the probability of getting depression for the second group. Okay, so let me say that again. So this means that the odds of getting depression is lower for the person number A compared to person number B, because the odds ratio is less than 1, or you see the coefficient is less than 0. Okay. And so how would we know whether the beta is 0 or it's bigger than 1 or it's bigger than 0 or whatever this is? We have to fit the model. And what your statistical software will be doing is that it's performed some estimation method, which you call maximum likelihood. It's not a focus of this, but most of the GLMs, the estimation of the methods, how they get these parameters based on your data, is based on a procedure which you call the maximum likelihood estimation. We are not going to be go through the mathematical details, but what is important is that usually this is done using the software. So most of the softwares would actually be giving you the estimates based on the maximum likelihood estimation methods. There are other estimation methods which I will talk about when I am concluding the whole of this training that are also available that one can use, but they have different approaches to how they estimate the values. Okay, so So now we understand we are not, it's not all the time that once we have data, it's not all the time we are going to go through this procedure. I'm only doing this procedure once so that you understand why anytime I fix a logistic regression, I don't interpret the betas, the coefficients directly. The message here is that make sure that you take the exponent of that coefficient. The exponent of that coefficient is called the odds ratio. And to interpret the odds ratio, you need to have what? Understand what is the risks for those that are, which group of people are you interpreting? Is it group A versus group B, or is it group B versus group A? William, your hand is up. Please go ahead, unmute and go ahead with your question. Williams Jr., please go ahead.
Thank you, Samuel. Would you please repeat how you subtracted from logit PA minus logit PB? Because I thought it had to be logit PA minus logit PB is equal to 1, but you concluded it with beta 1. Would you please repeat on that?
Oh, sorry, I was muted. I'm saying that, Williams, that we are taking this minus that. That gives us the left-hand side. The right-hand side, this minus that would give us 0. But here, this is 1, beta 1, and then this one is 0. So beta 1 minus 0 will give me beta 1. Is that clear now?
Sure, it is. Thank you.
Okay. All right. So like I'm saying, this is I'm just doing this so that you understand why when we are interpreting logistic regression, we need to understand what we are interpreting. Okay. So we would often look at the coefficients when we fit the model. If the value is negative, then it means that the odds is bigger for one group than the other. It is lower for one group than the other. And then if it is bigger than 1, or if the coefficient is bigger than 0, then it means that there's higher risks. And then if it is 0, then it means that the risk is the same for the two groups. So let's see let's consider this particular example. Assuming that I have fitted a logistic regression model, like in the previous one that we did. And then I have the coefficient. You see that I'm not talking about the beta 1, the beta 0 that we have here, because no matter what you do, the beta 0 will disappear. They always cancel out because it's just a constant. So in terms of the parameters, I'm not focusing on the beta naught, but I'm focusing on the coefficient of the independent variables. So the beta 1, assuming that when I estimated, I got 0.02. For beta 2, I got minus 0.5, which is the gender. In this particular case, I have to define what gender is because gender is not a number. So I can say that maybe male is 1, and then female is 0. All right. No, female is 1, and then male is 0. And then the income, maybe I estimate the coefficient of income and it is 0.01. Now, how do I interpret it? I can look at the figures and then I'll see that for age, it is 0.02, but the number is positive. So a positive number means that if somebody increase in age, the risk, because it's positive, it means that the risk is higher. So if an increase in age would mean that the risk would be higher than somebody who is at a particular age. So we often say that it means that a unit increase in the age will lead to an increase in the depression. Okay, but here this is because it is positive. It's giving a direction that it's going to lead to what higher risk. Here the value here is negative. It means that when I do my odds ratio, it's going to lead to what lower risk between what I am considering as what is 1 for gender, it's female, and then 0 for male. So it means that it will be higher for it will be lower for males than for females. And then here it is also positive, so that means that the risk is what? It's higher. So how do we interpret? So for gender, the coefficients, remember we said because it's a logistic regression, the first thing that we do is that we take the exponents of the coefficients. So when we take the exponents, which you can punch on your calculator, you'll find that the value is 0.61. Okay, so that means that if we want to interpret this, we will say the odds of getting depression is lower for females than for males. How much lower? It's about 61%. So if I multiply this one by 100, it's 61%. So it means that the risk is 61% lower for females than for males, and that is how you interpret it. Because the odds ratio, it's less than 1, as you can see. Because I take the exponent of a negative value, the value here will be less than 1. So less than 1 means that the risk or the odds, it's lower for the females than for males. For income, I'm going to say for every unit increase in income, the odds of having depression would increase by this quantity. All right. So remember, if we increase the because this is positive, that is why we are having an increasing factor, because we are going to multiply any number that you multiply by 1 times something, it's going to increase. So that means that the odds for that quantity would be higher. And then finally, for age, we'll also make sure that we interpret it after we have taken the exponent of that coefficient. Because it is positive, we are going to get a value that is what? Bigger than 1. Okay. And then you can see that this is surely bigger than 1. So it means that the odds of depression is going to increase for every 1 unit increase in the age of the person. So it means that as long as the people are aging, then their chances of getting depression is likely to increase. And that is how you would interpret your logistic regression model. Is there any question or comments? Remember, you can always put your questions on the chat. I can read it out and then I'll address it. Or if you want to speak, you can just unmute yourself and then mention and say your question. Okay, good. Now we are done with a lot of theory, trying to understand the concepts. How do we interpret the results? We want to now see something more practical. All right, we want to see something more practical. So we are going to use this motivating example to do the illustration. So I'm going to consider a sample data set which is coming from the 2022 Demographic and Health Survey DHS data from Kenya. All right. So in this survey, DHS is usually a household survey that is conducted. So in Kenya, it was conducted by the Kenya Bureau of Statistics. And in this particular round of survey, they had specialized questionnaire that assesses depression and anxiety amongst respondents. So it's self-reported depression and anxiety status. I'm going to focus on the depression data. So how did they ask the question? The respondents were made to give a medical history. So they respond to a question like, has a healthcare professional previously diagnosed you with depression or not? So that if they have ever been diagnosed or been told that they have been diagnosed with depression or anxiety, then they respond to this questionnaire. Okay. There were also other questions that relate to the treatments of these conditions. So that data is available for people to request through the Kenya Bureau of Statistics. And if they want to do some analysis about it, I think that data is would be available to them. Now, because of data protection issues, I'm not able to share with you the actual, because I don't have permission to share that data. But what I can do is just to randomly sample some of the respondents' data so that we can use for this demonstration. So the data would be shared, if not already shared with you, and some codes in R, which we would use to run this data. Okay. Now the data has 12 variables. The first variable is the ID, which is just some randomly generated numbers. That is the ID of the respondents. We also have age group. So age group, we have the age of the respondent that is grouped. We have sex, which is the sex of the respondent. We have the occupation of the respondent. We have the residency of the respondent, whether they live in rural or in urban areas. We also have some medical conditions, whether whether they've had hypertension before, yes or no, whether they have had diabetes before, yes or no. Their household wealth quintile information is also available. Their exposure to radio or media, it's also provided. So there is some information about their exposure to radio, TV, internet. Is your exposure to some of these things, can it cause depression, or do you get depressed because of that? Some questions like that can also be assessed if you have this kind of variable. And then we have the main outcome of interest, which is the depression status. So the depression status, which is answering the question about, do you have depression, yes or no? So this is how that data that we have will look like, so that we, when you have it, you are able to understand the name of the variables. So DMB means diabetes mellitus status. Wind X means wealth status. Radio means whether you are exposed to radio. TV means whether you are exposed to TV, etc., etc. HTN is the hypertension status, and depression is just representing our depression status. Okay, so the R codes are made available, but I've also tried to capture them in the slides in a way that we can actually follow through the slides without going to R. But then we can also go to R and run it so that we can see the results in real time. Okay, so in R, the data is in CSV format. Okay, and it is called depth kdhs.csv. Okay, so we can read in this data into our R using read.csv. Okay, I'll go through the slides, but maybe in the next time I would open the R console, and then we can all run it together from there. Today, let's just go through this like this, and then we can do the practical sections later on. If I want to see the dimension, so once I read this, I assign it to an object called dat. Okay, and then if I say dim dat, I want to know the dimension of the data. So if I say the dimension of the data, it tells me that I have 9,399 rows, and then I have 12 variables, as I have indicated. So that is how the data is structured. And then I can look at the first few rows of this data set by using the command head of the data. I want it to produce just the 5 rows. If I want the 10 rows, I can just put 10 here, and it will list all the 10, the first few 10 data points for this. So you can see that if I see the ID, I have ID 14144 134 21 52 1 as the ID variable. And then so for the first person, he belongs to the age range 30 to 34. The person is a male. In terms of occupation, he's a skilled or manual person. He lives in a urban area. He does not have hypertension, no diabetes. In terms of wealth index, this person is in the rich category. How often radio? He said at least once he listened to radio. This person less than once, etc. And then the depression status of this person is a no. Okay, so it gives you a fair idea about how the data is structured. So I can perform a very simple descriptives of this data. For now, I'm just only going to focus on the depression, which is my outcome variable, and then my independent variable is going to be sex. Okay, and sex is either yes or no. Yes or no. And the depression status is also yes or no. So if I want to describe this data, there is an R package which we call Arsenal. I'm sure the Man U fans will not be happy, but that is it. We have a package called Arsenal, which we can in R, which we can use to do very simple descriptive statistics. Yeah, I can see the Arsenal fans. Yeah, we are here. We are here. And we are happy that we have a package that is named after our beloved Arsenal. No more comments, Manchester United and those Chelsea fans. Sorry, but you don't have a package called that. So that package is very simple. The way Arsenal plays their football so simply. And the package is called Arsenal. Once you install it, you can use it to perform some descriptives very simply. So for example, we have a function in that package called table by. And then this function, I specify the outcome variable, which in this case is depression. So I'll put depression, and then I'll put this tilde symbol, and then I'll put sex, which is the independent variable. Okay. And then I'll specify the name of the data. The name of the data is that. All right. And then what statistics do I want to produce? I want the package to give me the number of missing values, the number of observations, and then the counts of the rows, and then the percentage. So it should give me some descriptives about the percentage. If it was quantitative data or independent variable, there is also an option, another argument which you can specify give you summaries of the categorical variables, numerical variables. And then I can tell it that I want my results to be displayed in terms of 2 decimal places. So I also specify digit is equals to 2L, and it will make sure that if I have decimal numbers, it will just reduce it to 1 decimal place. Okay. And then I can use summary tables. Now this function summary table, comma text is equals to 2. You can also use that to summarize when you run this, the output that you get. If you want to see the summary, then this is how you do the summary. Okay, so just a summary tab, and then whatever analysis was done in the first line would be displayed here. So here, how do we interpret this? You see that there's gender here. It gives us the number of observations. It didn't give us the number of missing values. It means that there are no missing values for this particular variable. Gender, you will see the male and the female, which are the levels of this category of this gender variable. And then it tells you that, okay, in this data, there were 4,901 who did not have depression. And then 146 people, which represent 2.9%, reported having been told that they have depression. Overall, it also gives you the overall value, totals. So that this number of people were females, and then this number of people were males. And then it also gives you like the p-value, which look at whether there is a relationship between depression status and gender using the chi-square test. And here it says that the p-value is 0.1, which is very big. So it means that actually there is no significant difference in terms of depression status between males and females. And you can see from the percentages that the depression status for female is 2.9%, and then that of male is also 2.4%. So statistically, they are not that different, and that is what is reflecting in terms of the p-value. But this is just the descriptive statistics. So yes, Teresa, your hand is up. Teresia, Bonnie, please unmute and go ahead. Teresia, please unmute and ask your question. Your hand is up. If you're having challenges unmuting, just give us a chat. Okay, so we cannot hear from Teresia. All right, so let's continue. When she's able to connect, then we can allow her to ask her questions. Yeah, so here again, remember, this is just artificial. It's just randomly selected samples, so this does not reflect the depression status of males and females in Kenya based on the DHS. So this is, remember that when we are interpreting these results. Okay, now this table just gives us the chi-square test to establish relationship between depression and gender, but we can still apply logistic regression to be able to do that, to also answer that question. So we want to see whether the logistic regression would give us results that are also consistent with whatever that we have done. Now, how do we fit a logistic regression using R? Remember, in our data that we described, the depression status was yes, no, yes, no. Yes, no. R does not know whether yes is 1 or no is 0. But it requires that your outcome is binary. So we need to tell R which one are we trying to model. Are we modeling the 0 or we are modeling the 1? Are we interested in the depression, the probability of depression, or we are interested in the probability of no depression? So we have to create a new variable such that we can tell it that if the person has the says yes, then give him a value of 1. And if they say no, give it a value of 0. So that is what we have done in this line of code. I'm saying that $y means that create a new variable in this data set called y. And then in this data set, this new variable called y, anywhere the depression is yes, give it a value of 1. Anywhere the depression value is 0, is no, give it a value of 0. So once I do this, a new variable will be created in my data that is just giving me y is equals to 1 and y is equals to 0. But then I know that 1 means yes, you have depression, and 0 means no, you do not have depression. Now, once I have done that, for the independent variable side, I don't need to do anything. It's only the response that I need to tell R exactly how I am defining my outcome. Which one is the yes and which one is the no. For the other side, we can leave it as that and still run our model. Now, to run the logistic regression, remember logistic regression is part of the GLM, generalized linear model. And there is a package in R called GLM. So it's makes it very easy to fit all our GLM models. Then we specify our outcome, which is Y, the new one that we have created, which is representing our depression status. Tilde, which is on your keyboard on the very top right corner, which it says that it's called a tilde symbol. And we use that to separate the independent versus the dependent variables. And then we specify what the independent variable is, which is 6. And then we tell R where the data is coming from. So the data is called that. Okay, so the data that we have described is called that. Now we need to specify that we are fitting a logistic regression. And we tell R that we want to fit a logistic regression by specifying what we call the family. So remember, we said that the GLM is made up of a family of exponential distribution. So the exponential family of distribution. So the exponential family of distribution means that the GLM package can handle all the various members of the exponential family. So we need to specify which of the members. So here, the members, because we are doing the logistic regression, the member here is binary. And then remember that in the binary, we also need to know what the canonical function is, right? The natural parameter is. And the natural parameter is also what we said that is a transformation. And we use the length function to transform the mean response. So here, once we specify that we are dealing with binomial, we can tell it that even though we are doing the binomial, we are interested in the length function, which is called the logit. If I want to fit the logistic regression with the probit link, all I need to do is just change the same model, but I'll change the logit here to probit. In that case, fitting a logistic regression binary outcome, but then the link function, which is transforming the mean, is going to be what? A probit instead of a logit. We are using the logit because we want the interpretation to be based on the odds ratio. Okay, and so that is why we have specified the logit. And then we close the function, the GLM function that we open the brackets, we close it. And then once we hit run, we save the model as model 1, and then we can summarize our data. So the summary will summarize what the logistic regression has given us. So we will see a number of results that are displayed by the software. We can see some values here, which is deviance residuals. We would see what these residuals mean later on. But then we will see that it also produces the coefficients. But now we know what the coefficients represent because we have seen how we formulate a logistic regression. Okay, so the intercept here, the beta naught, is minus 3.5, and then the gender, which we specify, is minus 0.21. So from this, what can you say about the sign of gender here in terms of how do we think in terms of having a negative value? What does this lead tell us? Anyone wants to comment on what does the negative 0.2 represent? You can put it on the chat, or you can just unmute and just tell us. Moema, do you want to say something? Lenny, Moema, do you want to tell us what the negative sign here is telling us about sex, male, or anybody? Come on. Where are the R guys? We'll stop very soon. I know it's a very packed day, but we'll stop very soon so that we can continue later on. But let's just finish with a simple logistic regression, then we can stop for tomorrow. Yes, anybody? Somebody bold enough? Where are the men and the bold men and women in the chat? Okay. So, okay, somebody says that So someone says lower risks. Somebody says yes, Samuel, the coefficients not meant to be exponentiated. Yes, but I'm not talking about the exponentiation yet, but we still can use the sign to tell what to expect. And so yes, so the correct response is, yeah, all those who are saying that males would have a lower depression rates. Yes, that is correct. Males would have a lower risk than females. Yes, so that is correct. So the negative sign here, even though we are not going to be able to interpret it, but it gives us an idea that the risk is going to be lower for males than for females. Okay, and so that is what it means. And then there are, it gives you the standard error of those estimates, and then it gives you the p-value. So the p-value here, we can see that it is 0.106. Okay, you remember when we did the chi-square, what was the p-value? The p-value for the chi-square test was also exactly 0.106. Okay, so you can see that we almost got the same p-value when we did the logistic regression and when we did the chi-square, establishing the relationship between depression and gender. So here, it means that they are all giving us the same conclusion, okay, which says that even though males would have a lower risk, but that relationship is not statistically significant. So that is why we have a not significant p-value. And yes, you are right. Now, if you want to interpret them in terms of how do we quantify the strength of the association, assuming that it was significant, and we want to interpret how much is the risk between males and females, then we'd need to what? Exponentiate the results. And in R, there is a very simple, you don't have to do the exponentiation yourself. You can tell R to do it for you. There is an R package called EpiDisplay, which we can use. In that package called EpiDisplay, so a list of packages has been given to you to install. So use today to install all of those packages so that when we go through the we are running the R by ourselves, we'll be able to understand all the various packages and procedures very clearly. And then there is a function called logistic.display in that library or that package. So we can just say logistic.display and just put model 1, the name of the objects that our logistic regression that we have fitted. We call it model 1. So we put model 1 into as the argument for this logistic display function, and then it will give us some results. So you can see that it tells you that, oh, it gives you the odds ratio for sex. Odds ratio is 0.81, and it gives you the 95% confidence interval. It gives you the p-value as well, okay, which will not obviously be different from what we have already seen from the p, because we only transform the results. We did not transform the p-values or anything, so they will still all give you the same values for and then there are also some other quantities that it produces. It gives you a value for AIC, which we'll talk about later, a value for log likelihood, which is also given here. Okay, so based on this, who can interpret, give an interpretation for what this odds ratio, how would we interpret this odds ratio? Not using the interpretation that I have specified here. There are so many ways in which we can interpret our odds ratio, and this is just one version. Yes.
Less likely. You can say they are less like, or 0. They are. It's like 100 minus 81. That is 19. So males,
Okay.
they are 19% less likely to
19% less likely. Yes. So we know that it is less likely because the value is less than 1, right?
Oh, your slides are gone.
Are they? Maybe it's from your side. Is
Yeah,
everybody experiencing that?
I actually entered the building, so I entered another building, so I'm sure maybe the network.
Yes. Okay. So you are
So they are
right.
less likely because it's less
They are
than
less
one. Yeah,
likely
less
by,
likely.
so
So
their risk is 19% lower for males than for female. Yes, Peter Mokaya, do you want to give us an alternative interpretation?
I think the what I can add is to comment on the confidence interval. When
Okay.
when the confidence interval is from 0.63 to 1.05, so we see in between the confidence interval there is 1. So it means
Yes.
there's the relationship is closer to 0. So
It's
when you
closer to
said when
0.
you and when you do exponent 0, you get 1. So also it shows that the relationship is not significant because of that confidence interval and also the p-value. That's what I can add
Great,
into
great,
what you've
great,
already said.
great
Yeah.
contribution, Peter. Yes, so just to reinforce what Peter have said, it means that when you also look at the confidence interval, remember we were using the cutoff of 1. If the value is greater than 1, we have higher risks. When it is less than 1, we have lower risks. And if it is equals to 1, then the risk is the same, all right? Or so here, when you see that the interval is having 1, because it's the odds ratio, then like he's mentioned, it means that there's no relationship because it's almost the same. So if you say the risk is the same for males and females, you are basically saying that there is no risk at all, or it means that the relationship is not significantly different. And that is what is reflected in the p-value as well. So just to mention that, yes, you can always use the p-value, but you can also look at your confidence interval to be able to interpret whether, in fact, the relationship that you are observing is actually significant or not. Fikru says females are 1.2 at risk of developing the disease. Okay, so she has reversed the relationship and she thinks that females will be 1.2 at higher risk for the disease than for males. So this is also another way you could interpret it, but that would be a bit complicated. You can always just pick the coefficient. If you wanted to interpret it in terms for female, then you make sure that you set females as your reference. You set male as the reference level in this. So I'm going to talk about the reference level probably tomorrow so that we understand what I'm talking about. So then it means that here we would set female as the male as the reference. But you see that the results that was displayed by R sets it specified that sex, and then inside as alongside sex it's added male. So it means that this coefficient is for male, but the female is set as the reference level. And then we'll talk about why that is very important when we try to interpret this later on. Okay, so this would be the last slide for today's section. And it's supposed to be a group assignment. I don't know if you've already formulated groups, but I want you to go through the slides that we have done today and try to address this question. Suppose that we want to predict the likelihood of somebody getting readmissions of depression patients to a hospital within 30 days. And then the following information has been provided. You have patients' demographics, medical history, clinical variables. Discuss within your group. Use like examples, hypothetical data. Discuss how a logistic regression will be applied to identify high-risk patients who are likely to be readmitted so that you can target them for specific interventions. And then also from whatever you decide on, try to specify how would your logistic regression, how would it be specified? And then just assume some coefficients. Let one person just pick a value as the coefficient for each of these variables that you have specified and see whether if you have some values, how would you have interpreted that? Okay, so I guess we have done almost like 2 hours already. Joel, can we stop here for today? Is Joel still with us? Yeah, so before we close for today's lessons, just revise whatever we have done for today. The concepts that we are going to be using are going to be very similar, even for the other type of models that we'll be doing, like the logistic regression. I brought in the aspect of the exponential family and you know, the length functions and things like that for completeness, because I know there are some who may have statistics background and they want to understand why we do some of these things, and that is why I brought in those aspects. But the rest of the classes, if it is not, it will just be about the interpretation. It will just be about getting the concept, the intuition behind it, and just giving you that kind of you know, flavor in terms of this training. So don't be discouraged that there's a lot of complex maths in it, but you would see that I was just skipping most of the things that are not relevant, just focusing on the most relevant aspects that you need to think about when you are fitting your models. So if there are no questions, we'll stop here and continue, I think, tomorrow. Williams Jr., you have a hands up if you want to say something. Freddie
Yes.
also has the hands up. Yeah.
Thank you, Samuel, for the beautiful presentation. For my case, I'm very conversant with the Python. Would that be okay if I use Python?
Yes. So if you can use Python, you can just try. So we'll give you an assignment that whatever examples that we are fitting, try to see whether you can fix these models. Everything that we do in R, also do it in Python. When we are done, you can share that with your colleagues. Okay, so that those who want to do Python can also do that. I'm still a beginner for Python because I do everything in R, even creating my slides. I create my slides in R. So I feel like I don't need all the other software. So I've been very slow in, you know, getting myself into Python. But yes, unless I only go to Python when it is really needed. So I may not be providing codes for Python, but take it as a challenge, Williams, and try to replicate all the things that we are doing. And then anytime you spot that there are differences, just prompt us and tell us that, I'm getting these different values from Python. And then let's try to understand where the differences are coming from. Will that be okay for you?
Yeah, sure thing.
Okay. Freddie Nyada, you have your hands up. You want to say something?
Yes, I hope I'm audible.
Very much.
Hello. Okay, I had a similar concern with the one Williams had, but I think you have sorted it out. Number two, normally most of the presenters, as they present their data sets, normally they share them via the Google Drive or something like that, plus the presentation. So we were asking if we could have those resources over the drives, maybe. Maybe you could communicate with Joel for that. Otherwise,
yes, so that is
you.
why I needed Joel online to respond to that because I have shared all these materials with him.
I think unless maybe some of you missed, I've seen some comments from some people who did not receive the material, so I'll share again. So no worry about that.
Okay. So you are all sorted. The slides will be shared. Okay. Are there group formation for groups? I don't know. Joel, could you also comment? I thought some of them came in as groups that may apply for the grants or things like that. Are there existing groups already that they can? So the group works. I'm not going to. If a group decide to work on something and want to see whether they want to have my opinion about some of the things that they have done, they can just share it with me privately for me to give them feedback. But apart from that, most of the activities we will try and do it together in the course. But I'm fully available in case a group wants to discuss, or even individuals want to discuss maybe some concepts that are not very clear, or some examples that you need to get feedback from me. I'm very much willing and available to support in that direction. Joel, over.
Okay, sure. For the groups, some of them are joining as groups. So because we have some people who formed the groups, but we are not aware of the groups because we let the participants form their own groups. What we did is previously we had some matchmaking sessions where we just allowed the participants to know each other and to introduce to each other, maybe to get to know what fields people are working on and what maybe they want to work on. But on the groups themselves, we are not really following up on them. So in the capacity building here, like they are joining more of like as individuals. So I know maybe some people organize themselves. I saw some of them commenting, trying to ask their friends to join the training, but we are not like following up the group formation. So yeah, so maybe for the groups we are not able to share resources to specific groups, but we have the contacts to all the individuals in the capacity building program. So if we have like materials, we can be able to reach out to them.
Okay, yeah, I think that is a great addition. So like I've mentioned, just if you have existing groups, discuss these things within the groups. If you are individuals, try them on your own. If you need to get feedback, what I can do also is that in the beginning of the next section, all group activities, I would ask group members to share with me or to the everybody what they have done in terms of the group work. What were some of the comments, ideas that they came up with, so that we'll be able to discuss together and learn from each other. Okay. And then I think there was a question that I missed from the chats by I think it was Theresia, about some column percentages that were supposed to add up to 100. That I believe it is the last column of the descriptive statistics that you mean. Yeah, if it is the descriptive column, I am not reporting the percentage of male and female. What I was reporting is in the depression, the prevalence of depression amongst males and females. So it is not column percentages, but it's more of row percentage, which tells me what is the prevalence of. So I'm not interested in the percentage of males or percentage of females, but depression the depression levels. And because I use row percentage, the last column would still be 100%, because it is only looking at the percentage for that group, male or female. I hope that answers your question. Okay. All right. Is there any last comment from anyone before we drop off? So make sure that you have access to the slides and things that I have shared, so that tomorrow we can have time to continue more on this. I wish everyone a very good evening, good afternoon, wherever you are, and I hope to see you again for more exciting sections going forward. Over to you, Joel.
Thank you very much, and I think that was quite a wonderful session. So we continue tomorrow, and then we'll also have another session on Friday. So see you tomorrow, and I will share the materials again on the email. So the same email you receive the invite. So I'll share a link for this course. So I'll see you tomorrow, and bye-bye, everyone.